Now next we're going to state a rule that we can prove using the axioms, and it's done in the book, but we'll just state the result here. This is what we call the addition rule. The addition rule is kind of an extension or a generalization of axiom 3. Axiom 3 applies only to disjoint events. This addition rule applies to non-disjoint events. Okay? So this rule says the probability of A union B is P of A plus P of B minus the probability of their intersection. Now, you may ask, why do we have to subtract? Well, the basic idea here is we subtract so that we don't double count anything. So to illustrate what this means and how to use the addition rule, let's look at this last example. So what we have here in this table at the bottom is the results from a professor who gives his students some review problems to do before a test. Hey, that sounds kind of familiar. And each student either completes the problems or did not complete the problems. And this table tells us that 42 students completed the problems, 38 students did not complete, for a total of 80 students. Okay? Now, the students took the test, and the professor recorded what everybody got. A total of 46 people got an A or a B, and a total of 34 people got a C or below. The numbers in the middle of the table tell us that 34 students got an A or B and completed the problems. 8 students got a C or below and completed the problems. 12 students got an A or B and did not complete, and so on and so forth. Okay? So what we're going to do here is randomly choose a student from this group of 80, and let's let E denote the event that the student did not complete the problems, and F denote the event that the student got a C or below. We want to calculate the probability of E or F, E union F. Okay. So let's look at one right way that we could do this problem. And we could take the theoretical approach. We have a finite sample space. Everything is equally likely, so the theoretical approach applies. So E union F is the same as saying a student did not complete the problems or got a C or below. And so what we could do is simply count the number of students who did not complete the problems or got a C or below, and then divide that by the total number of students. Well, the total number of students is 80, so that part's easy. Okay. Now to get the numerator, we got to look through the center of the table and count the number of students who got a C or below or did not complete the problem. So if we look here, these 34 students, they completed and they got an A or a B. So we're not interested in those students. These 8 students got a C or below. So we're interested in those, so we're going to count those. These 12 students did not complete, so we're going to count them. And these 26 students did not complete. They also got a C or below, so we're going to count them. And so the total is 8 plus 12 plus 26. We divide that by 80, and we get our final answer of 0.575. So there's one right way to calculate this probability. Okay. Now let's look at a wrong way to do it. What we might be tempted to do is to use axiom 3 and say that, well, union means addition, so let's calculate the probability of E. Probability of E is the total number of students who did not complete the problems divided by 80, so 38 over 80. P of F is the number of students who got a C or below, 34 divided by 80. And so then we just want to calculate or add those two probabilities together to get 72 over 80, which is 0.9. But the problem here is that this number double counts these 26 students who got a C or below and did not complete the problems. So we don't want to do that. We don't want to double count those. So another right way to do it is to use the addition rule, where we calculate these probabilities P of E and P of F just like we did before. But then we also need to calculate the probability of the intersection. So we take 26 students who did not complete and got a C or below, divide that by 80, and then we add and subtract to get 46 over 80, which is 0.575, which is the exact same answer we got using the theoretical approach.